Okay, so last time we talked, actually I can start with announcements. Assignment coming up today, I know I've said it was gonna be out for days now. My apologies. If it were the longer one that is the one after this one, then I would feel worse. But this is a fairly short and the 16 question assignment. I think it's the second shortest one so far.
How much of it is context or something on that?
Some of it. Okay. Yeah, so I anticipate wanting to meet with people to go over that in fairly significant detail. All right. So that's yeah, question.
Yeah, review framework 3, I remember you said something about that, is that still on the
Yeah,
table?
that is still on the table. I will probably have that due either next week or the week after.
Okay. Was it the entire thing or just like set problems, like a helping with the problems and that kind of stuff?
I'll probably make it the entire thing, just because it seemed like just about everybody struggled with that. All right, yesterday we talked about countable and uncountable sets. We found many sets that were countable, and we found a set that was uncountable. Which was very interesting because we're going to start diving into a lot of the uses of this concept. Actually, I'm going to quickly reset this because I thought I would have to see the screen. That is better. So we found that we can prove that countable sets are countable by making an enumeration procedure. So given we have the current element, what is the next element? And then we have an argument that there is no element in the set that is not reached by that enumeration. So that's the two parts of a countable set. Give the enumeration, provide an argument that says that no element of this set will not be reached by this enumeration procedure. We say it's an algorithm because we know that some algorithms don't terminate. And this process may not terminate, but we're able to at least reason about it in theory because it's deterministic. It's well defined, there will always be a successor, and there are predictable results, which means that we know what's going to happen far out in the future. We can reason about what it would be like theoretically to run this algorithm without actually running the algorithm. So we don't need to run it to verify the results, which is what a lot of math does for us. It allows us to reason about things without actually being able to do them, which is usually superfluous in computer science. But when we start getting out on the edges of theory, it starts becoming very useful because we will never be able to enumerate all of the positive integers. Can't do it. What this means about countable sets and the enumeration of countable sets is it also means that we can simulate this on a Turing machine or simulate it on a computer. So the concept of a countable set is very useful. Let's give you an example. We have an alphabet and a set. First question I ask you is the set countable? That is the positive closure of the alphabet. So one or more symbols of the alphabet. What do we think? Countable? Uncountable? We say count, 1 vote for countable, 2 votes for countable, including the one online. For those who say that it is countable, how would you do it? My argument is it is countable, but it depends highly on how you enumerate it. With a set like this, you can enumerate it in a bunch of different ways. So some of those will lead to countable sets, and some of those will lead to not countable sets. It's countable because there exists such an enumeration procedure, but what does that enumeration procedure look like? Maybe the easier question is, what would an enumeration be that is not reasonable, or would not lead to a countable set? What if I had you list all strings in the language in alphabetical order? What would that produce? A. We will continue to spit out new strings in this language forever. But that procedure will never reach B, or BA, or BB, or BC, or even AB. So we list all strings in alphabetical order. We don't get an enumeration procedure for this set because we can give a counterexample that this procedure will not reach ever. It'll continue to generate new strings in the language, but that procedure, there is a counterexample of something that procedure won't get to. So infinite number of strings that start with A's will never produce a string that starts with B, would be a counterexample of why this procedure does not work for this set. What could we do about this to make this set countable? If we go based on length, right? So we're going to produce all strings of length 1, and then all strings of length 2, and then all strings of length 3, and then all strings of length 4. We're still enumerating an infinite number of strings, but now there does not exist any such counterexample such that we won't get there. Any example that you give me will have a finite length. It could be an arbitrary length. You can give me a string that has the largest number that you know off the top of your head, number of characters in it. And I could tell you how many instructions it would take for that procedure to generate exactly that string. So it would take more instructions than the largest number that you know, but it's a number that exists. So now, by doing this in length order, we end up with something we can work with. This is worth talking about because we said that we could represent a Turing machine with some kind of bitwise representation. We just take the encoding of the internal states and the encoding of the tape, and we turn that into binary, and that becomes a Turing machine program. A description of a Turing machine that can be fed as input into another Turing machine. So, since binary is exactly like this alphabet that's just 0 and 1, and bit strings are that alphabet star, the star closure of that, we know that Turing machines are countable. We could just infinitely generate binary strings. Some of those will be legal representations of Turing machines, and some of them will not. But the idea is that that procedure will continuously generate more and more and more legal Turing machines that do something. Whether it's something that's useful or not doesn't matter. But that procedure would eventually generate any Turing machine or any algorithm or computation that you could write or you could produce. Questions about that? That's a really strange, abstract way of thinking of computation. But now we have a procedure that no matter what program you write, this procedure would eventually generate exactly that program. Questions on anything from this result? we're gonna move on to a concept called linear bounded automata. So we've seen that there is no easy way to extend the power of a Turing machine. Anything that we did to it, we said, you don't have to move left or right, you can stay. Extra tracks, extra read-write heads, a two-dimensional track. Anything we did to it did not actually improve the power of it. But another interesting question is, in what interesting ways can we limit a Turing machine? If we could limit things, maybe that opens up some abilities to increase the efficiency of acceptance or rejection of Turing machines. As we know, when we restrict things, frequently we get results that do that. They lead to more efficient results on at least some subset of the problems that, in this case, a Turing machine can solve. So we've seen examples of this. An NPDA is a non-deterministic Turing machine with a tape restricted to be interacted with like a stack, where we only have access to the rightmost written character or the leftmost written character, however you want to code that. So that is a restriction on a Turing machine, or it's a way to think of a Turing machine in terms of one of the automata that we've studied so far in the class. We could also limit access to a finite portion of the tape. So now instead of saying we have an infinite tape, we will say we have a tape that has 100 cells, or a tape that has 10,000 cells. This is, when we talked about regular languages, the equivalent of a simulation of a regular language. So a finite state machine had a finite amount of memory, which means the tape has a finite amount of space. So those are two ways that we can limit a Turing machine, and we get results that we have seen so far in the class. On the other hand, what if we limited the tape to just that of the input? We allow the input to be of arbitrary length, but whatever the input is, we don't allow the Turing machine to use any more memory than that input took. Intriguing idea. Any guesses on the restriction? Does that produce a language or a set of languages that is smaller than everything the Turing machine could accept or reject or work with? Is it an actual limitation? Are you able to do everything that a Turing machine could do if you have just that much memory?
I'm thinking like if you need to preserve the entire input, then you can't do anything else.
You'd have to modify it and find a way, a simpler way to store it. Or try to think of some fun examples, like if you had something in unary, you would have to invent some way to represent that unary using a different language. So we use decimal to represent our numbers. We can use a lot fewer characters to represent something in decimal than we could in unary. So my attempt to provide a counterexample isn't really gonna work too well, because I don't think that that fooled too many people. So the answer is yes, it's a restriction. But it's at least worth thinking about. Is there some way or some representation of a way to do that? We've seen that, we see this in machines when we want to zip up a file, for instance. It can take up less space because of how we store the internal representation of it. We can't actually run what's there without expanding it back out, but we at least have a way to save it for the future in a way that takes less space than it does when it's fully extracted. So, of course, still no bound on the size of the input. We need to be able to mark the left end and the right end of the input. The left end markers cannot be written and can't be bypassed. We'll assume that this is a non-deterministic Turing machine and can also have multiple tracks. That's another way that we could store the input for later. Each of them is bounded to be the same size as the first track. We just have to know how many tracks we have at the start. So it doesn't actually change if we have 2 tracks or 10 tracks or 100 tracks. It doesn't change the power of the automata as long as we bound the number of tracks. Let's take a look at an example. Find a linear bounded automata that accepts the language a to the n factorial. We're going to assume that this is written in unary on the table. So we're only going to have access to that amount of memory. The goal is to either accept or reject to determine are the number of ones successively on the tape a member of some n factorial. Any ideas for how we could do that? Can anyone describe a general approach that they might use?
I don't understand the concept of over here, not that it's following up.
Okay, so we don't have any more tape outside of the bounds of that unary. It doesn't matter if we have extra tracks or not. So I give you something like, is this input string some n factorial? And I give you 20 ones in a row. We know that 20 is not a factorial. So we have either 6, 2 times 3, 24, 2 times 3 times 4, 120, 2 times 3 times 4 times 5. So those we would accept, everything else we would reject between those values. So if I give you like 120, then you have 120 cells to work with. If I give you 24, you only have 24 cells to work with. If I gave you an input that was 79, then you would have 79 cells to work with. So you have an amount of input or an amount of space to construct your program that is based on the size of the input.
So are we just trying to find out like what, I guess that function of the input is to.
So it's either a yes or no. The number of ones on the tape is some factorial or not. Does that make sense?
I mean, like in general, like what are we trying to do all of more like what?
Doesn't matter what's on the tape, if this is an acceptor, so we're either going to halt and accept or halt and reject. The output on the tape doesn't matter. It's just a matter of, can you construct the idea of a program within the limitations of the size of the input? So we can't write anything until we have made space for it. But in making space for it, we have to save it somehow, or we have to make some kind of modification to it that is deterministic, where we know the state we're in is based on some aspect of this problem definition.
Are we, when they do another states we have?
No.
Say what?
Yes, it has to be bounded by the size of the input. So if I give you an input of size 53, all of the arbitrary number of tracks that you say you want are all bounded to have 53 cells. But I would argue that anything you can do on 2 tracks, you can do on 1 track. And you can do on 10 tracks, you can do on 1 track. Any ideas?
So we can have unlimited states, so I think it means we just like count upwards, say if we have our 1 factorial, turn that into an x, and then we look for, okay, we're in our next state, which says we're looking for 2 factorials to be an x plus the number of base 2 factorial, which not to an x, and just going.
Okay. Interesting. How would we? That would, so we need a finite number of states, but it's an unbounded number of states.
Okay.
So my counter example to that idea would be however many states you design, I design that many plus 1 factorial. I put that on the tape, and you would be unable to recognize that because you wouldn't be able to move up to the next one because it doesn't cycle back in some regard. That is close though. You have a run with that idea. What happens if you inverse what happens to a factorial? So we know that 120 is 5 factorial. What can we do to 120 to be able to show that it is some factorial?
Divided by, and then -1, then -1, -1.
How do we know that it's 5 factorial when we start?
Yes,
If it's not deterministic, then I guess we could, but there has to be a finite number of splits there. We can't say it's n factorial, so make n transitions between. There's no way to code that. There's no way to specify that. What do we know about the commutativity of multiplication though?
doesn't matter where you do it,
Yes, what does that tell us we can do?
do that but backwards.
Yeah, so take the input, divide it by 2. If it goes in, continue. Then divide it by 3, then divide it by 4, then divide it by 5. If you ever end with a single cell left of input, then it is a factorial. If you're unable to do the next step of that process, it's not a factorial.
How can we keep track later on, is it just about by 1, how time to divide by 2, keep going forward?
You can store that anywhere. You can take one of the cells as soon as you start removing that, and you can store the current number that you are on, or store something that does that in that respect, and tells you, read that, go divide by that, increment, read that, divide by that. So we have 120 on the tape. We're gonna go remove half of them in some way, shape, or form. So we're gonna start in a state that says, all right, the current value is 2. We're going to move to the end of the tape. Replace a 1 with a blank. Go back, replace a 1 with something that says that I've read that 1, an A. Go back to the end, delete, go back to the beginning, turn a 1 into an A. Delete, A, delete, A, delete, A, until you have 60 A's. Then you're gonna go back to the beginning and turn them all back to 1s. Increment from 2 to 3, now we have 61s on the track. So if this is a factorial, we should be able to divide this evenly by 3. So now we're going to go to the end, delete 1, come back, turn it into an A. Delete, delete, A, delete, delete, A, delete, delete, A. And you end up with 20 A's. turn them back into ones. Now divide by 4, delete, 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 A, delete, 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 A, and now we have 5. Increment. Delete, 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 A, and now we have a single one left on the track. That says that we started with a factorial number of ones on the track. So that's the general idea. We're gonna successively divide the number of A's on the tape by an increasing value. If there is a single A left on the tape, in fact, A to the n factorial. So they were ones, they were A's. So we turn the A's into ones, vice versa. Whatever we want to do there. You can use a second tape to keep track of the current divisor, or you could use the first cell that you delete. Doesn't really matter. So now the question I have for you is this concept of a linear bounded automata. Is it more powerful, less powerful, or equally powerful? Not compared to Turing machines, but compared to non-deterministic pushdown automata.
It's definitely more powerful.
What makes you say that it is more powerful?
Because I remember we had the example of A to the N, B to the N, C to the N. We knew that that was not context free from our previous thing, so we knew that an NP could represent that, but then we said that a Turing machine can't do that. And the algorithm that we went with, that I didn't need to write any extra space, but
Okay, I like that. So it can accept at least one language that an NPDA couldn't. Could it accept any language that an NPDA could accept? That's the second half of that question. I totally agree with you on the first part. The answer turned out to be yes. Anything that we could produce with an NPDA, we could produce with a linear bounded automata. So it is more powerful in general. We could show that the language of linear bounded automata is not context free by showing a pumping lemma and going through that process. Next, are they less or equally powerful to unbounded Turing machines? Are there any problems that actively require more space than the input can store?
say like and put it in, I'll put it again. And I'll do it on that for output that.
Sure, that seems like a reasonable example. So the answer is in fact less. And if you are curious about what that proof looks like, you should go look at it in the book. But Patrick gave us an excellent example of something that I think intuitively ties us to this idea. Take his input and A's and give us output and A's followed by NB's. You would need a second track for that. You could also, even if you said, all right, there's going to be a second track for the output, you could say, give n squared b's that follow it, or n to the n b's that, so you have a to the n, b to the n to the n. Now it doesn't matter how many tracks you have, now you need more tracks to represent the output. No finite number, there will be some size of A such that you don't have enough tracks if you have a finite number of tracks. Questions on any of that? Grab the next one. Everyone's good so far on everything we've covered? Ready to go. across the board. There we go. Cool. All right, so now we're really ready to start diving into all of the theory part of the class. I mean, granted, we've been doing a lot of theory in this class, but now we're gonna start talking about the actual limits of algorithmic computation and what kinds of languages exist outside of languages that we can write algorithms for, or algorithms that are guaranteed to terminate. So we want to be able to define classes of languages that have either practical meaning or theoretical meaning and are somehow distinct from each other. So like we talked about regular languages, context-free languages, etc., we want to be able to talk about some theoretical language classes or some important language classes of the ability to accept or reject certain languages. Diving into this, we're going to need to know everything that a Turing machine can do. So one classification, languages that a Turing machine can operate on. And another one involves some fun, saying any restrictions on grammars are gone. If you're thinking, I thought we already did that, we're context-free languages. Wasn't a context-free grammar, all restrictions of grammars gone? There is one restriction we can relax yet. And it creates a very fun class of language. We're going to start with the concept of recursively enumerable language. So let's give a definition first. A recursively enumerable language is one such that a Turing machine can accept it. There's one big asterisk at the end of this, and that's that we're not saying anything about a Turing machine rejecting a string in this language. There is nothing that says what happens if we want to say that something is not in this language. So a recursively enumerable language can answer yes, but may not be able to answer no.
So would that just be like an infinite?
Yeah, a program that went into that is, it continue to look for the answer and look for the answer and look for the answer in an infinite set. We don't know, we can't conclude that we haven't found it yet and we are never going to find it, we just know we haven't found it yet. If the answer is yes, it will terminate in a finite amount of time. But we don't know yet if the answer isn't yes yet, or if the answer is no. Which makes for a very annoying kind of algorithm if you're actually sitting waiting for your program to terminate. Because you can't actually answer yes. Right? You can if the Turing machine halts, or if your program halts, then you say the answer was yes. So we will allow a Turing machine to go into an infinite loop and never halt. If the query string is in a language, the Turing machine will halt in a finite number of transitions. For all strings not of the language, we may get a rejection. The Turing machine may halt and reject, or it may never halt. So that is the concept of a recursively enumerable language in overall. Have we seen a language like this before?
That would be a set of everything that we've seen so far.
It definitely is, yes. So it exists, everything that we've talked about so far is in this language, or is in this class of languages, as well as some things we've talked about.
So you're talking about like just something that's specific with this, but not anything else that we've seen.
So for instance, like a query for a program that would determine if the inputted integer is a positive integer. You can imagine writing a program that starts at 1 and continues to generate new positive integers until it either finds the query number or doesn't. You input some really large number, and eventually this program will halt and say, yes, it's a positive integer. You give it -1, And it will continue to hunt and hunt and hunt and hunt and hunt and hunt forever. There are always new positive integers to generate. It will never reject. But we don't know if we had no idea of what an integer was. You can imagine the obfuscation of, I don't understand anything about positive integers, and you're just waiting for your program to terminate or not. You wouldn't know if this is just some really far off into the distance value in the positive integers, or if it is not an element of the positive integers. You wouldn't be able to answer that question from your program's execution. If it halts, you know it's a member of the positive integers. If it doesn't halt, you don't know. We could just have not gotten there yet. Does that make sense? Another class is the recursive language, which can now answer yes or no to any problem, to any string in the language. So in a finite number of steps, it will accept or it will reject. This allows us to be able to say a membership. This allows us to find a membership algorithm that says, given a query string, we can tell in a finite amount of time whether that string is in the language, because we will get a for sure accept or a for sure reject within some finite amount of time. It could be a very long amount of time, but at least theoretically, it would accept, it would halt and accept or halt and reject. So this allows us to examine languages that there is no easy way to accept or reject, something like in our lifetimes. With the computers that we have in front of us, we could write an algorithm that is recursive that would not terminate for certain inputs until we are long dead. We can at least now theoretically think, is this language recursive? For any input, would it eventually halt and accept or halt and reject? So now it no longer makes sense to write that program because we run it on this input, we're going to be dead before we have an answer. But at least now we have a way to describe whether or not it would halt. And then sometime in the future, when we have computers that are billions, trillions of times faster than our current computation power, maybe it becomes something that is feasible to do. But we can now at least reason about what is feasibly calculable and what is not. First question I have for you, are all recursively enumerable languages recursive?
And just like reasoning through it, like why would they be separated into two different categories if they're the same?
Well, so it's asking basically, is one a subset of the other? Not are they different, because they certainly are different. But for instance, every regular language is context-free. But not every context-free language is regular. Because the regular languages are a subset of the context-free languages. So we have something similar going on here. Which is the subset of the other one?
It could be the other way around.
It is the other way around. So all recursively enumerable languages are not recursive. And are recursive languages recursively enumerable? Yes. If we just look back at the definitions, a recursively enumerable language is one that accepts in a finite amount of time and could reject in a finite amount of time or fail to reject. So if it rejects in a finite amount of time, then it is recursive. Now, we want to be able to enumerate these kinds of languages. We want to be able to write an enumeration procedure for languages that belong to either of these language classes. Let's say you have a language, or I give you a language, and I ask the question, is this language recursive? Or is this language recursively enumerable? You could reason about it. Now I say, write an algorithm that starts outputting everything from a recursive language. I would want, again, that to be in a full enumeration procedure that would eventually generate any given query in the language. So how do we do that for recursive languages? How do we do that for recursively enumerable languages? Let's start with the easier one. Enumeration of a recursive language. What does an enumeration procedure look like for a recursive language? Since we know that we can accept or reject in a finite amount of time, we can just make a Turing machine that does that. We're going to call that TM membership. If we can accept or reject in a finite amount of time, we can construct an algorithm that will do that. We can write a Turing machine program that will accept or reject. By definition of a recursive language. So if we want to make an enumeration procedure, we just design a Turing machine to continue to spit out new values of that language, new strings in that language. We then make another Turing machine that we call the generator. We then generate all possible strings composed of characters in that alphabet, and we will feed the output from TM generator into TM membership. So let's say I give you and ask, is binary a recursive language? We need some restriction on binary. Let's say all binary strings that start with some number of zeros and end with that many ones. So 0 to the n, 1 to the n. Is this recursive? Yes, it is. Why?
You're associated again, you an example if you have a class.
Yeah. So we read some number of A's, we map them to some number of B's. We can do that. So we're going to have the generator generate all binary strings. Starting with 0, then 1, then 0, 0, then 0, 1, then 1, 0, then 1, 1, then 1, 0, 0. All right, 0, 0, 0, 0, 0, 1. All binary strings could eventually be generated by this generator Turing machine. Every single binary string that we generate, we're going to pass into the membership Turing machine that will tell us, is this binary string in the form 0 to the n, 1 to the n? This would then tell us all strings eventually that are in the language. There are an infinite number of them, but the generator would eventually generate the next one. And the membership would be able to say, yes, that thing we just generated is in the language. There is no counterexample string that you could give me of the form 0 to the n, 1 to the n, that the generator would eventually generate and pass to the membership that would eventually accept. So this is a general algorithmic process for enumerating recursive languages. We just write two Turing machine programs, the generator and the membership. When generator is done, it writes the output of the generator onto membership's tape. Then membership writes onto some output track only the accepted strings. Once it accepts, it goes and writes that string on some track. And now we have some way of spinning, calculating, writing a new string in the language. Calculating, writing a new string in the language. Questions on that? Does that make sense? We can map that to any recursive language. So in general, that is the process that we are going to use. It is much harder for recursively enumerable languages because we cannot possibly generate something that we would eventually go into an infinite loop to reject, because then we would have failed to generate the next string. The membership Turing machine is now never going to terminate and never be ready for the next input. So any ideas about how we could enumerate a recursively enumerable language? Be able to generate all possible legal outputs in that language? We've actually seen the solution to this. That's my hint to you. We've seen it recently.
That limit on the length strings again?
That would work for all strings that are less than that. So I guess you could kind of think of it as a breadth first search. It's like generate everything of length 1. But there's nothing that says that even a string that's of length 1, if it's rejected, doesn't go into an infinite loop with our membership. But it's a very similar idea. How did we output all of the rational numbers?
Denominator and then draw as squiggly.
Yeah, we did a diagonalization where we went through all numerator is 1, then numerator is 2, and we changed the numerator and the denominator by 1, and then we did another one where we did that. How would that process be able to help us in this world? What are the 2 dimensions that we would want to have a diagonalization for? The dimensions turn out to be a list of query strings and the number of transitions that we've done in that calculation so far. So here is an infinite list of all strings in that the TM generator would generate. So all possible strings that could be in the language. We don't know yet. But we're going to simulate the first move on this. Then we're going to generate the first move on this. Then we're going to go back to the state that we were in this, and we're going to do the second move on this string. Then we're going to move to the third string, do the first move there. The second move on this, the third move on this. The fourth move, the first move on this, the second move on this, the third move on this, the fourth move on this. So it's a very similar idea to now, if this is going to accept in a finite number of steps. So let's say this is in the language, and this would be accepted after 10,000 transitions. You would eventually get there. If W2 goes into an infinite loop, it doesn't prevent us from getting to W3 or getting to W10,000. Regardless of any string that's in the language, if it is accepted in some finite number of transitions, we will get there eventually, which tells us that we can now enumerate a recursively enumerable language. We can generate any given query string that is in a recursively enumerable language. That never means this process won't terminate, but it will continue to generate new strings in that recursively enumerable language forever. And not get stuck. That's where we're going to stop for the day. hopefully this was at least somewhat intriguing in a theoretical sense. It's really out there. But it is the limits of what do we do when we are severely restricted on how we can write programs to answer some questions. We need to be really creative about the programs that we write. So we'll pick this back up tomorrow. I will run back to my office and get your assignment up for the week. I also have office hours starting now. If you want to go over any of this material in more detail, I'd be happy to draw it out, give you some more examples, etc.
Assignment due next week?
Next week, yeah.
Next week, Thanksgiving week?
I think so. It's the week after.
We got,